So did y'all have a good weekend? Lots of fun?
I did a leg day.
You did leg day? Take your frustration of your... So I was joking around about how I could see who procrastinated versus who didn't by who's like barely staying awake versus who's like, yeah, I'm fine for help. So, okay, yeah, so I've started the meeting. So,
I did section 3 on Sunday, and it took me to like 5 o'clock.
I did that. I started section 3 because I thought that was like Friday. I did it on Friday night and Saturday night. Like I started with those. I was like, yeah, let's go ahead and do that first.
Yeah. So just so you all know that I'm not a hypocrite when I say I went through things like this when I was an undergrad. Those of you can see on the screen, this was my take-home exam that I did my last semester of my senior year, and it's just a mere 35 pages. Yeah. Yep. So you could, if you're like, oh, Dr. Morse was so bad, you could have Dr. Ranga like I did. Yep. So the question he asked for problem 3 was so complicated it took me 18 pages to write. Or sorry, 16 pages. So that was problem 1. So I had to do all these diagrams and for Huffman encoding, and then so basically Lempel-Ziv is the algorithm that's used to compress and decompress for WinZip and all those programs like that. And he just said basically for sizes 4, 8, 12, and 16. And this seems simple, but it turns out you have to describe step by step and show the steps through decompression. Well, that is all of this. So I wrote code that did it. Yep. And that's what he expected for a full, complete answer. Like,
that's kind of like, how many pages was that?
I believe it was 10. At least for number 6, I gave you guys 40. So it was. So, and I lost a half point because you know the dynamic power equation where it's effective capacitance times VDD squared times the frequency, right? So if you look right here, I have forgotten to do this. If I'd done that, I would have gotten a perfect score on the exam, but I did not. So he docked points. It's like, damn it. So.
I was doing this 5 o'clock in the morning.
Well, he made the exam out of 50. So. But after that exam, I was a mixed undergrad-grad course where I was the only undergrad. It's like this course, but the exact opposite. We have one grad student. And I got the highest score, and it was by, I want to say, like 12 or 13 points, like substantially so. And I had a job offer that I wasn't really happy with, and I just wanted to go talk to him. It's like, this VLSI stuff really kind of makes sense to me. And so I went in, everybody else in lines in front of me complaining about their exam. And I'm just sitting there going, oh, shut up, man. And he sees me come around, and he has this really deep baritone voice who became my PhD advisor. He goes, why are you here? You did very well. Why are you complaining? I was like, oh, I'm not complaining. I just wanted to talk to you about life and things. So he had this PhD offer out to this student in China who hadn't responded to him in 2 months. And he's like, well, I'm going to take that from him. Would you like it? And so that was the exam that changed my life. And so, the reason I tell you that is, one, to let you know that when you oftentimes when you're a student, you kind of get this idea that professors don't respect your time. And to a certain extent, they don't. But not going to lie. But at the same time, I want you to know that I'm not a hypocrite, that I've been through the same thing. And that part, putting forth that kind of effort made a profound difference in my life. And I do sincerely hope, from going through the resume and preparing for it and being able to see the process of preparing for an interview, that I do hope that in some way this does have a positive effect on your life. I know it was hard now, but especially, that Intel job, a couple of you went online and actually looked it up. That I didn't make that Intel job up. That's a real, and you all are qualified for it, right? So you can be like my friend Ransford, who took days preparing for it, or you already have half of your job preparation done, right? And well, no, you will have whatever. By the time they call you, you'll have completed the course. So, okay, so on that note, for number 6, how many of you remembered that on the last lecture where I uploaded a video, I actually worked through and did the answer? A couple of you are going, "Oh my God, really?" Like I had the exact numerical and like I worked through it on the screen. Like I came up with the question number 6. Yeah, exactly. So people are coming up to me and going, "I spent so much time on number 6." I'm like, "Oh no, oh no, I gave you the answer."
Like look at that other 48 or 18.
Yeah.
2 of them, they are like different portions of it.
Yeah. Mm-hmm.
Well, I went on sites like
And I
on my answer, like every question I put like lecture 9, lecture 8, number 40 minutes. So,
yeah. So oh yeah, and I didn't upload the last video lecture because I didn't want you guys to think that you had to do those TGOs as well, just to remove the ambiguity. So okay, mean mug. Because as I told George this morning regarding respecting students' time, I do ask you guys to work hard, but I like to think I know where the line is. And had I asked you to do yet another homework assignment, that would have definitely crossed it. So yeah. Yes.
yeah.
Oh, okay. They weren't due.
No.
I can. I'm willing to do that. Did anybody else turn in the homework assignment from last lecture? I'll figure something out. You went above and beyond. I'll reward extra effort. All right. So on that note, yeah, George is like. No. The one from last lecture that I didn't upload that you were asking that you didn't do. Yeah. Okay, so on that note, we're going to start section 4. So up to this point in the course, we've really discussed cell design and how does the cell impact when you tie cells together. What we haven't really talked about are everything in between these cells, these interconnects. And so this section, we're going to be talking about power consumption through the interconnect. So I have included this quote from Texas Instruments here. The reduction of power consumption makes a device more reliable. The need for devices that consume a minimum amount of power was a major driving force behind the development of CMOS technologies. As a result, CMOS devices are best known for low power consumption. However, for minimizing the power requirements of a board or a system, simply knowing that CMOS devices use less power than equivalent devices from other technologies does not help much. It is important to know not only how to calculate power consumption, but also to understand how factors such as input voltage level, input rise time, power dissipation capacitance, and output load affect the power consumption of a device. So if you wanted to, you could actually go to this document that Texas Instruments posted here, which is probably shorter than some of your exam submissions. But it talks a lot about the different concepts of power consumption. So for those of you who see inverter mode and static power consumption, you recognize that. So basically, they're parasitic capacitance, you now understand that. So, and diode voltage. We're going to go into diode voltage and Boltzmann's constant today with static and dynamic power consumption. So what is power? We've talked about power consumption, static and dynamic power consumption, but this is tying everything back into all the concepts we've talked about so far. We define power as the work done on charge carriers between a potential difference in a circuit over time. The SI unit for power is the watt, and it is joules per second. And so for energy, then energy is just the rate of power consumption, and you find the rate of power consumption by taking the integral. So you can make a mental note of that for those of you who are in Dr. Daigle's class and he tries to incorporate integrals and series into all the stuff for control theory. It's a good mental note to make. And so average power consumption is just that integral over time. So you have some sort of power function, right? So x would be power, or no, this would be time, and this would be power of time, right? So you have some sort of power consumption graph. And so when you're doing this series, you're just trying to split it up and try to add them up over time, right? And the integral is just taking this total value, and then the average power consumption is just summing everything up, right? And then dividing it by the amount of time. Because when you're doing a series, you're splitting it up into slices. So if you have summation of I of t, right? And that translates into your integral. And then you divide it by t, by the number of slices. So this is I equals 0 to uppercase t. And you divide it by t, that's the number of time slices. So here, you're actually just dividing it by the total amount of time. An average power consumption of a circuit is a very important metric. Typically, what you'll see in a power consumption graph is you see big spike and then kind of steady, big spike and then steady. And the way that correlates is you have your rise and then fall. Right? So most of the power consumption is consumed during switching. So that's why that's why we're going to differentiate between static and dynamic power consumption. Your static power consumption is the result of a lot of leakage current and all your parasitic capacitances, because you're basically just holding the value. When you're switching, that means you're actually putting a different set of values on the gates of the transistors and creating an inversion region for which to flow, or in the other pull, if you're creating the inversion region in the pull-up network, you're closing the inversion region in the pull-down network, right? So that's where takes a lot more power. And that's why, if you recall, you guys have done Quine-Mikulski reduction, right? Quine-Mikulski, K-maps. Why is it important? Why is it physically important to be able to reduce logic? Because the more logic you reduce, the fewer switching, the less switching you're going to have. The less switching you're going to have, the more reduced power consumption you have. So all the stuff you learned in electronic circuits and logic circuits, it wasn't all for naught. And so power generation, I've included the power generation. I'm going to scroll past 4.1. I hope everybody has it. So here, what we're going to do is we're going to combine these two equations. The power generation is just, P equals IV. You all know that one, right? And then power consumed by resistor is V squared over R. So we can solve that up for I squared R. So now, if we recall, how do we take these diagrams that we have here and correlate them to CMOS transistor design? A lot of it has to do with these capacitances, because we know that we're creating a distance either through our silicon dioxide, or we have our gate capacitances or parasitic capacitances that we've discussed before. So we start here. We state that the energy of the circuit is equal to the rate of the amount of power over the unit time, and then we plug in our power generation equation. And then we have, remember that I equals C dV dt equation that we had earlier? This was a TGO from section 2. So we can start taking advantage of that. We can plug that in to our equation. Oh, so I don't want to scroll too fast. So we can replace the current here with C dV over dt. V of t d of t. Well, those are going to go away, right? And if we replace this, and it's going to become, capacitance will be a constant, so it comes onto the outside of the integral. And so from 0 to VC, integral of the voltage over dV, and that becomes CV squared over 2. And that correlates to the energy. And that's our proof. So that's how in a CMOS circuit we're able to relate the capacitance, all of these capacitances within a transistor, to the energy and power consumption of the circuit. Does anybody have any questions so far? All right. So here's what happens. When the gate output rises, so that means we're going from a logic 0 to a logic 1. The energy stored in this capacitor, we have to worry about the energy on the input and output. These should be squared, by the way. So with the energy drawn from the supply, we use the same equation. I apologize, these should have squared over 2, right? Oh, I'm sorry. That's how this happens. Okay, so we use the same idea, right? And then what's going to happen is when we're switching from 0 to 1, we have to worry about where the energy is actually being consumed. So what is actually physically happening? So this is where we're tying in the mathematics with our understanding of how the pull-up and pull-down networks are doped. So when we go from a 0 to 1, what's actually happening is we are creating this inversion region here in the PMOS transistor, and we're cutting off the NMOS transistor, right? And so when we go from 0 to 1, what's actually ends up happening is we need to create the inversion region, and then the capacitor is going to hold this value here, right? So we have output capacitance, which we calculated using the Elmore delay from last section. And we know that's CL VDD squared. And we do this by canceling these out. And VDD is going to also be a unit, right? So what's going to end up happening here is C and VDD come to the outside because they're constants. And the load capacitance times the supply voltage times the unit integral from 0 to VDD of dV over dt. So that these cancel out. So it's just the integral of dV. So that becomes V, which of course we know is VDD. So CL VDD squared. And we know from the previous proof that, I'm going to scroll back up here for a second, the energy of the capacitance of the transistors CV squared over 2, right? So what this means is half of the energy from the supply is dissipated by the PMOS transistor in the situation where the gate output rises, and the other half is stored in the capacitor. Does that make sense?
What are the effects of all the parasitic capacitances?
We'll get there.
Okay.
Yep. Yep. Just push the I believe button for right now. Hint, it requires you to consume a lot more power. So then what's going to happen here in this note, when the output gate falls, so that means we're cutting off the PMOS transistor, we have the flow through from 0 to the output. So that means what's going to happen is we have our output is at 1, right? And the amount of time it takes to fall, we have our regions. We have VI. And we have to fall from a rise and fall region in order to hit our noise margins. Well, the capacitor is going to be, its job is to hold a charge. So it's going to be trying to hold this up as long as possible. So that's why you're going to get some sort of dissipation time. And in order to know your amount of dissipation time, that's how you're able to calculate the speed at which you can actually calculate how fast you can actually run the computer chip. So that's why what we did last section involving Elmore delay becomes so important. Because in order to charge this capacitor, you eventually have to figure out how long it's going to take. And as a result, that allows you to properly design your circuit. So when I took CMOS, we had to design a thermometer that had to run at 1 kilohertz, which seems easy until you start having to mess with it. So in my group, we were able to prove that our design worked at 12.6 megahertz. But the key thing is, how do you prove that? You prove it by using these equations and then actually doing simulation, which is what you guys will be doing in the last 3 weeks of the semester. I have a set of labs that you'll be able to work through. It won't be it won't be anywhere near as complicated as the one I did in CMOS, just because they had another lab credit that you guys won't get, so therefore it's not appropriate to ask you to do that level of work. So instead, I'll just have you do step-by-step labs that'll gain you experience with the tools.
I don't know if I might be jumping ahead, but does that also factor into the slew rate?
To the what?
Slew rate?
Yes. You are jumping ahead. There was like, what's slew? Yep. We'll clock slew. We'll get there. So at this point, because of the fact that we have half of this dissipated in the capacitor and half of it in either your pull-up or pull-down network, we have to worry about, we want to officially separate out static and dynamic power consumption. So your static power consumption when the circuit is not changing voltage. So simply put, as I described a little while ago, you have your static power consumption, and this is dynamic power consumption. And so the Paddock's tower, so you have the sub-threshold current plus your gate current plus your junction current. So all of these, remember, so you have our basic current here, and that contributes from our different capacitances. So we have to worry about junction leakage, gate leakage, and subthreshold leakage. So this is part of the answer to your question, Demba. And the reason why it's like this is because there's no actual switching going on. So everything is just trying to maintain your inversion region in pull-up in whatever network happens to be activated. So as a result, everything that's going on is all the factors that are fighting your ability to do that. And these are the main three. And so if dynamic power consumption occurs while the circuit input switch and your switching power plus your short circuit power. And then we'll go into that, what the short circuit is actually here in a second. So from, I think it was number 4, where you had to basically, for a 2-input AND gate, be able to prove what happened here. So this short circuit current is basically section C. Remember, they're both kind of in the middle and they're both on simultaneously. So there's going to be these brief moments when you're doing your pull-up and pull-down network where both are on simultaneously. And you've proven this. And that is a specific moment where you consume a fair amount of power. That's why you get these boop, boop. If you look at power consumption circuit diagrams, which I'd be happy to show you sometime, that's more or less what they look like. And so this is the actual switching frequency proof. So when we talked about the average power consumption for switching is your amount of energy, which is the integral of your supply current and your supply voltage from 0 to t divided by time. And then supply voltage is a constant, so it comes to the outside, so it's VDD over T, the integral of from 0 to T times the supply current. And then we have our time times, where we have CL dV over dt. So putting that in, cancel out. And then the proof comes out to your load capacitance times VDD squared times the switching frequency. And so that's how you're able to come up with the actual dynamic power consumption that we've presented before. So that's how it's actually proven.
What's the big T?
The big what?
The big T.
Time. Yeah. Oh yeah. So basically, okay. So that's just, let's make sure I'm very clear about how I'm describing this. So we have it correlates to the period, but in this case it's time. So here it starts here and ends here. That correlates to, the reason it's not a period is because you have to worry about, right. Mm-hmm. So. But as you see anyway, when you get down to the final equation, all the times cancel out because of the way we're substituting in. Is that how the capacitance switching frequency correlates as well? So what ends up happening is that the way you relate is the frequency of the switching. So that period that you were talking about, Trey, that's where it comes into play right here. Now, another way that it comes in is this concept of activity factor. So it's not just your frequency switching, but you're not always going to switch. It's not going to switch every single time on an output, right? So let's say you're running an inverter and it switches 1 to 0 to 1, and then it stays at 1 for a good long time. Well, we know that this is static power consumption, static power consumption, static power consumption, static power consumption. And our dynamic power consumption occurs here, here, and here, right? So the amount of dynamic power consumption, not the amount of power consumption that we have in the circuit, is not only reliant on the fact that we know the frequency, but how often it actually switches. And so 4.9, the activity factor is the probability of the circuit node transitions from a 0 to a 1. So let's think about from the concept of an OR gate, right? So you have your truth table, right? And then your outputs are 0, 1, and 1. And 1. So what's the probability that's going to switch from a 0 to a 1? So if we calculate it out, you can, if it's a 0, it's going to be 1 in 4, 3 and 4, right? That it's going to go here to one of these. The 1 in 4 is just going to stay there. But then you actually have to worry about, well, it's not going to switch from a 1 to a 0 in any of these cases. If it's at 0, 1, it's never going to switch from a 0 to a 1 because it's already at 1. So the probability becomes relatively low, right? So that's how the switching factor comes into play. And so what ends up happening is we're going to add a little alpha symbol. So remember, so the switching factor is 0.5 for an inverter, right? So if you have 0, it's going to switch to a 1, but if it's a 1, it's a 0. And by definition, when it transitions from 0 to 1, when it's a 1, it's never going to happen. So half the time it's going to be a 0. So here, 100% of the time, 0% of the time, then it becomes 50%. And so that becomes where 0.5 comes into play. So what ends up happening with an OR gate is it can switch from a 0 to a 1 in 3 instances. But there are a total of 16 instances where it can change on an output. It can go from 0, 1 on an input to 1, 0, and it would stay at 1. Or 1, 0 to 1, 1, and it'll stay at 1. So your switching factor for an OR gate is actually going to be 3 over 16. Does that make sense? Okay. And that is where, when you recall this equation that we came up with, 1/2 CLVDD squared over F, that's where that came from. So that is your switching power of an inverter. And so recall in I think it was problem 6 where we talked about Elmore delay and everything's compared to a unit inverter. We're going to see over and over again is that with everything, the inverter is just the base unit for which you can measure everything else. And it's a good idea to kind of relate how that ties into your inverter, because what happens if you tie 2 inverters together, you get a buffer. And if you basically have a device and you're reaching like 90% of your noise margin regions, right? You can actually put a buffer on the output as long as you size it properly, and it will get it back to 100%. So a lot of people will put buffers on the outputs of various cells and devices in order to be able to restore the logic, as long as you size it properly. So you're going to see over and over again all of these activity factors, Elmore delays, tied back into a unit inverter as a size. So recall the energy here, CLVDD squared. We tied them all back in, and so that's why they end up being the same here. Okay, so kind of walk over the same thing. Determine the activity factor for the signal shown below. So this is an example of where it doesn't always switch. And so what ends up happening is we have 4 transitions. Okay, so the clock rate is 1 gigahertz. And we have a signal here that switches 1, 2, 3, 4 times, right? So it makes 4 transitions in 10 nanoseconds. So if we recall the activity factors, which switches from 0 to 1, right? So that matters. So we have 2 transitions that qualify for the 0 to 1 here and 0 to 1 here. So those are the appropriate transitions. So it makes 4 transitions in 10 nanoseconds, and we count 2 transitions as a cycle. That just becomes 0.2, right? The easiest way is I could have done it's 2 transitions in 10 nanoseconds, and it would have been. That's a simpler way of coming up with the exact same answer. Does anybody have any questions before I continue? All right. So all these different waveforms here. So this is actually, I'm going to zoom out just a tad. So this is actually a really good comparison of what happens when you have all the different factors that are going on when you have switching. So in this case, we have a signal. that's starting at 1, switches to 0, switches back to 1, right? So what's actually physically going on here? So we have this output. I'm sorry, come on. So this is your input signal, and this is your output signal. And as you can see, what's happening is we have a strong signal, and it gets slightly degraded on the output, right? So we have some sort of reaction that results in all of our capacitances. It gets up to 1, and we have some kind of delay. And so our output is 1 over C, the integral of IC dt. So what's actually happening? Here we have current, right? So these are our different factors for current, and here we have power consumption. So this is how everything ties together. So here, what's going on is that as the switch happens, so here's switching, where it's going so fast, I know, right? So we have our PMOS and NMOS current, right? So this current is what's going through our PMOS transistor. So in the first switch, it's actually, we hit our saturation region, and then they hit the linear region. And then once we hit this point, 0.6, we're kind of hitting our, our short circuit current, right? And then same thing, when we go from 0 to 1, what's ended up happening is everything's going fine. You see this little blip here? The actual, the dominant amount of power consumption is what happens when you're switching from a 1 to a 0. And here, from 0 to 1, it's being dominated, the current is being dominated by the PMOS. And the reason why, you see how we're going from a 0 to 1 on the output here? So it's actually happening at this time, we're activating our PMOS transistor. Oh, I'm sorry, yeah, we're activating our PMOS transistor because we have the output. And then here, what's happening is we're turning the transistor off. And what's going to happen is we now have current going through the NMOS transistor during the switching. So the primary is actually like create the amount of current it takes to actually, we have power consumption here, right? And that's because we're actually turning the transistors on and off. And you can see the same thing, this short circuit current here for our PMOS transistor. And we have the same thing, we have a short circuit current here for the NMOS transistor.
Is that like that place, is that what actually causes like bouncing in switches?
Yes, exactly. So that's why we have to be very careful about how we size our PMOS and NMOS transistors relative to each other, because what does happen is if you don't, you get a lot of this. So if you see something like that, you're actually consuming too much power with the other circuits. And ideally, you want these two to consume approximately the same. You see, this is a well-designed inverter because you see how the power consumption here and here are identical. That's ideally what you want. And so what ends up happening is we also we don't just worry about the PMOS and NMOS transistors, we also worry about the capacitors. So here we have our current from our, let's see if it's, sorry, it's not playing super nice. Okay, so we have our capacitor current, right? So here it's 0, and then we have positive and negative current, right? So here our PMOS transistor is activated, and here our NMOS transistor is activated. So then the power consumption is this V out times that. So here we're the same thing, we're multiplying it by 1, so forth, right? positive and negative. And then we take the integral of the power consumption to get the total energy of the capacitor, and you can see the rate of change over time. And then these are the voltage being dissipated at the supply voltage. I'm sorry, the power being consumed by the supply voltage. And the reason why you see it here is because we have the spike when we're activating the PMOS transistor, and then we have our little short current bump there, and then the energy there. So if you're struggling with some of the concepts, this diagram here is a good one to go over, because it kind of sums up how everything's working together in terms of current, power consumption, voltage, input and output voltage. You see how there's, all these factors contribute to a slightly degraded signal.
So for the short current for both PMOS and MOS, is there like a standard range? Is there like a standard range that you have to be in, or does that like depend on the customer? I know you want it as low as possible, but
Right.
Is there like kind of a max range that you don't want to go above?
You do not want it to go in. You do not want it to exceed your noise margin. So you have that 10% noise margin.
Mm-hmm.
You don't want it getting to an instance where you're actually going above it, because once you're going above it, you're actually compromising the output value. Yes. Okay, so let me scroll down here, and I'll be able to show you this whole 4.2 question. There we go. Okay, so we have a digital system on chip, for example, 4.2. And so now we're tying all these different factors in: lambda, logic capacitance of the logic transistors, memory. So here we're actually tying this back into computer architecture, because we have to deal a lot with switching of memory versus logic switching, right? So memory, if you recall, MIPS, we have we only do load and store to put it into the cache memory, and everything's done with local register copies. One of the reasons we do that is going to be demonstrated here in this question, because not only does it take more time to do load and store, but as you're going to see, I'm going to give you a preview here, the capacitor, the memory capacitors, because they have to store information, consume a lot more energy of your SRAM and your DRAM right there. So we have a chip here with 1 billion transistors. So now we're in the VSI level. Now 50 million of them are logic gates, and the remainder are memory arrays. So the average logic transistor is 12 lambda and has a switching factor of 0.1. So it will take 10 clock cycles on average for any logic gate to switch. The memory arrays are divided into banks, and only the necessary bank is activated. So if we recall again from 385, we used set associativity. One of the benefits of set associativity is reduced power consumption. So all we have to do is activate the one that we need to be able to get it. And so the average memory transistor is 4 lambda, and alpha is 0.02. So we only want to switch 2 times out of every 100. Assume each transistor contributes 1 femtofarads per micrometer of gate capacitance and 0.8 femtofarads of diffusion capacitance. Estimate the switching power when operating at 1 gigahertz. So we basically break this down in 2 sections. We have our logic gates and we have our memory gates, right? So we have 50 million of those, so that's where we get this number. And then what I did is it's a 1 billion transistor chip, so I have 1 billion minus 50 million here for this unit. So that's the number of transistors. So then the second part is to multiply it by the transistor size, which for the logic gate was 12 lambda. And if you recall our unit size here, 0.25 micrometers per lambda, because it is a 25 nanometer chip. I mean, it's a 50 nanometer channel with lambda is 25 nanometers. So what we're doing in this part of the transistor is we're saying we have 50 million transistors. Our lambda design rules, we're saying that's 12 lambda, and we know based on that's a 50 nanometer channel that it's actually 0.25 micrometers per lambda. So now we're back to a unit here. And so we have gate capacitance and diffusion capacitance, which we sum as 1 plus 0.8 femtofarads per micrometer. The micrometers go away. And now it comes out to be 27 nanofarads when you use the calculator. Same thing with the memory. We have 1 billion minus 50 million, so we have 950 million transistors of memory. And we defined the memory transistor as 4 lambda. And again, we know that our lambda is actually 25 nanometers, which is half the feature size. These cancel out. And then again, it's 1 plus 0.8 femtofarads per micrometer. These are going to cancel out the units. And that comes out to 171 nanofarads. So if we want to calculate the switching power, we have to know our switching factors, and we need to know the supply voltage and the frequency and the load capacitances. So what we're going to do for the total capacitance is we're going to split them up here like so. We know the switching factor for the logic arrays are here, right? So that's where we get this number. 27 nanofarads comes from here. Same thing, we know our switching factor is 0.02 for memory, and we calculated the memory capacitance to be 171 nanofarads. So we sum them up, and that gives you your total capacitance. And then we know that 1 gigahertz is our switching, and we were given at the beginning of the problem that's a 0.15 volts. I mean 0.1 volts. And so this allows us to relate how often a device switches with the specific gate and diffusion capacitances, as well as the switching frequency in order to be able to determine our switching power. So does anybody have any questions about that? Okay, so example 4.3. You're synthesizing a chip composed of random logic with average activity factor of 0.1. So it switches once every 10 cycles. You are using a standard cell process with an average switching capacitance of 450 picofarads per micrometer. Estimate the dynamic power consumption of your chip if it has an area of 70 millimeters per square millimeters and runs at 450 megahertz at VDD is 0.9. So here we just kind of start plugging and chugging. So we have our equation. We know our switching factor is 0.1. we know our load capacitance is 450 picofarads over millimeter squared, but we know that we have to get to picofarads, so we need the area, which we are given as 70 millimeters squared. So we just multiply these together, and those will cancel out. Right? So then you just VDD squared, just 0.9, we're given that here, and we're also given the frequency as 450 megahertz. Thought you were all copying down the answer. I realize you're probably copying down 4.10. Okay, so let me ask you this question. So 4.10, why do you think this is important to know? Fundamental switching probabilities. And so I talked about just the switching probability of an OR gate, right? And that's 3/16. But here we've defined a 2-point OR gate as 1 minus the negation of probability of A over the probability of B. The whole point of this is that it's not just, we don't just worry about the local circuit, we have to worry about the previous inputs, right? So if this is, the probability that A is going to switch and the probability that B is going to switch, well, that's going to contribute to the probability that we're actually going to get a switching on the output. So here, remember, all probabilities are between 0 and 1. So here they've calculated as not A over not B, right? So here you have 0, 0, 0, 1, 1, 0, and 1, 1. So the probability is going to switch is half and a quarter. And so here I give an example down here. Let the probability of node of I is equal to 1. Therefore, not P is 1 minus that. So 0.5 times 0.5 is 0.25. And so the inverter example is P is 0.5. So therefore, your switching factor, your probability activity factor is I times P of I. So this is and, right? Sorry. So here's our problem, example 4.4. We're given a 4-input Nand gate as designed on the left. So recall we can actually design them in different ways. So we've designed a 4-input Nand gate using 2 Nand gates and with inverters here and a Nand gate on the output, like so. Estimate the switching probabilities and activity factors if each node at the inputs has probability of 0.5. So basically, what we're saying here is that if you have an inverter and its probability of switching is 0.5, and the probability of it actually switching on the input is half, then the probability of it actually becoming from a 0 to 1 is 1 in 4. So here's how the question works. The probability is going to be, we take our equation for the NAND gates, right? 1 minus not A, not B. And if you recall this gate here, I actually used this. Remember, what is this? What can this be substituted as using De Morgan's law? Not A, not B becomes.
Or not, not,
Yeah, this is what I have circled right here. So this is A, B. I don't know why the ink's taking so long, but there we go. Not A, not B. There we go. Now it's starting to draw. Not right. These are the same. So recall this one. Remember, AND gates require an inverter on the output. Plus, we require 2 more inverters on the inputs, right? So that requires 4 transistors plus 2 transistors plus 2 transistors plus 2 transistors. So it becomes 10 to do that. Or you can do it with a NOR gate with 4, right? So as you can see, this equation here becomes the same as this one, right? Sorry, I don't know why the ink is not cooperating with me so much here. So I did that there, right? There you go, that's better. And so we plug that in, and we get we defined our probability input probabilities as 0.5 and 0.5, right? So that becomes 0.25. This becomes 3/4. And then PN2 is C and D, right? So that becomes 3/4 and 3/4. And so 3/4 times 1 over 3/4 here, which is where we tied this in before, right? That becomes 3/4 times 1/4, which becomes 3 over 16, which we have intuitively proven before, right? And then recall that De Morgan's law, as I was giving you that hint there. And so the probability, Pn1 and Pn2, is 1/4 times 1/4 as a result. Right. Oh, yes, right, because it's 15, 16, this is 1 minus. Right? We see up here, we have the equations. Let me scroll back up here. I see where I might be confusing you guys here. So here we have NAND gate. The input's going to be 1 minus, and the other one's just the multiple. So as a result, we then take this last part here about activity factor, because we had to find the activity factor, is this times 1 minus that. So that becomes 1/16 times 15/16, which becomes 15 over 256. So, okay, it's 9:50. Up to this point, we've talked about, okay, well, these are the switching factors, and these are what happens when you allow them to switch, and this is the power consumption that you have. Oh, I should ask, does anybody have any questions before I move forward?
So N1 and N2 is if you were ORing?
Yeah, so so here we're trying to calculate out N1 and N2, right? So here we're trying to calculate N1 and N2. So Pn1 and Pn2 correlates to our probabilities that we have A and B, right? So here we define each of these as 1/2. So then the probabilities tie in here and so forth. So first things we have to do is we actually have to calculate this probability and then this probability. And then we take these probabilities and figure out how they tie into the NOR gate on me. So you can put a NOR gate here, right?
I'm so confused with a 1/4 times 1/4 function.
Okay, so that's kind of what. So n probability of n1, probability of n2, right? So here, what's the probability? Yeah, that happens here. Oh, go back. There we go. All right, so here we have to calculate the probability that's going to switch from a 0 to a 1, right? So we use our equation. We have 1/2 and 1/2, right? So it becomes 3/4. So then P2 is going to be the same thing. So we're getting 3/4 here. So what does this actually mean? So when we go back up here to our fundamental switching probabilities. So we have our switching probability, but then we have to deal with what's going to happen in the case of switching from a 0 to a 1. So in this case, we have a Nand gate. So Nand gate means that we have logic 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, and 1, 1, 0, right? So here, we're going to worry about it can switch from any of these instances, right? But from here, switch there, here can switch there, here can switch there. Those don't count. So the number we calculated out here is by taking 3/4, which is probability that we calculated out here, and then the negation of pi, which is 1 minus 3/4, which is 1/4. That comes out to 3/16. So that means we've calculated this out properly because we intuitively know it's 3/16. So that's the switching factor. So here's the, okay, I see what you're asking. So here we have to worry about PN1. Why did I put 1/4? That's a good question. 3/4, 3/4. It should be 3/4. Yeah, this should be, okay, all right. Yeah, so we calculated, I see, I'm an idiot. Okay, no, I did it right. All right, so we go back to the NOR equation, right? And it's not PN1 and not PN2. So here we calculated as 3/4. So it's 1 minus 3/4, which becomes 1/4. That becomes 1/16, and that becomes, yeah, that's, hold on, should I zoom in a little more so that becomes more clear? There's that, that's a little too far. There, you can see it better now? Okay, yeah. So that becomes this value 1 minus that value by using that table. Oh, no. Oh, sorry. No, that's not.
Yeah, okay.
And if we find the switching factor of the whole thing, it's 15 over 256. Now, if we actually did it 4 input, I'll do the first 8. Oh, no, I'll make these all 1 to make it. If we had 1, 1, 1, 1, it's the last one, right? So this is a 4 input, and this one's all 1, and the rest of these are zeros. So there's going to be 15 different possible input combinations for a 4 input NAND gate, right? And so there's 15 possibilities that any of these zeros are going to become 1s. But since there's a total of 16, you can actually go from any combination to any other combination, including itself, right? So that just becomes 16 squared, which is 256. So there's 15 possibilities that can go from a 0 to a 1, and 256 total possibilities. So this number that we just calculated out is intuitively correct. Okay, any other questions before we move on? Yeah. Okay, so what your question is that these are proven equations, right?
Right.
So what we did to solve that last problem was we used this one here. So we calculated that out as 3/4, right? So the first thing we did was we had two NAND gates, 1 minus PAPB, right? So that became 1 minus 0.5 times 0.5 here. It became 0.25, that's a 2, and that became 3/4.
Right. Those are NANDs, right?
Yeah, the first parts were NANDs. So then what we did is we substituted in a NOR instead of using an inverter, an AND gate, and another inverter, right? So we used De Morgan's law to then say, okay, so remember, not A and not B is this equation here. So let's say, okay, so a NOR gate, right? Let's say that the probability of switching is half, 0.5, right? And we know that to be so if we just draw out a truth table. So 1 minus 0.5, 1 minus 0.5 becomes 0.25 because that's 2. And we actually figured that out, right? So that's 1/4 because we know that there's that probability. So that comes out, I mean, that is so.
So is the first line equation for the example, is that written incorrectly then?
No, the everything's written right. So this that's written correctly. You have a conceptual error. So this first part is for the NAND gate,
Right.
which is this. Right? And so PN2 is just the same thing because it's also, I was just being redundant because it has this C there, right? So this calculated PN1, the probability is going to be 3/4 and 3/4. So then what's going to happen is the activity factor is PN times 1 minus PN. Because the probability is going to switch times the probability it's not going to switch. So that becomes 3/16. And we've actually shown intuitively that this is correct. So then what's going to happen is now we worry about the probability before this gate. So we have an inverter, we have a NAND gate, and we have another inverter. Or what we do is we just do De Morgan's to get to our NOR gate, right? So the NOR gate in the table was actually not A, not PA, not PB. Oop, that didn't quite cooperate. From our table. So then we use that equation to figure out the probability here. So we calculated this out previously as 3/4, right? So this is 3/4 and 3/4, right? I mean, intuitively, this should make sense because we're switching from a 0 to a 1, and we have 3/4 and 3/4. We say 1 minus. That became 1/4 times 1/4. So we got 1/16 on the output here. And then the switching factor, we use the same equation. Activity is probability times 1 minus the probability. So that became 1/16 times 5/16, right? Which we then came out to 15 over 256. So for the AND gate, for the 4-input NAND gate, remember that big table I drew up just a moment ago? That is how that's intuitively correct. So this solution is written out correctly. I didn't understand exactly what Josh was asking about once I realized what he was asking about. Oh, you're talking about that.
So basically, you're doing
Yeah.
Emulate the whole inverter with the Nand Gate to get
What we have proven here in this last line 15 over 256, we have proven that the probability of the A, B, C, and D inputs are 1/2, that we're actually going to get the correct switching factor on the output. So if you recall, we actually had different designs of 6 input NAND gates from the last problems in section 3, or you can do different inverters. You can actually screw up the designs where the switching factor is bad. And if your switching factor is worse than the theoretical switching factor, like we actually calculated out as 15 over 256, and this design is correct, that means you're going to end up consuming more power than is necessary. So how do we reduce some of this power? Clock gating. So basically, we're trying to save clock activity and eliminate all switching activity in the block. So basically, we have a little circuit that's going to actually cut the clock off from the circuit. And what's going to end up happening is that the power is not going to consume any, obviously the circuit's not going to consume any power while that circuit is running, right? And so the last line, this requires determining if the block is going to be used. So there's going to be logic that you have to put in there. So reduces power consumption, but you're going to gain some area. And so if it ever scrolls, here we go. All right, so clock gating ANDs a clock signal. So we have our clock signal with, we talked about that logic before, to turn off the clock to idle block. So what's going on in this, it's only the definition, it's not the drawing. Basically what's going on here is we have, if the clock is on and the enable logic is on, then we turn on the circuit. Otherwise, if the clock is off, then the register is off. Or if the enable logic is off, then the registers are off as well. And so B and A, there you have a grad 4.1 there. And I think this is a good place to stop. So that next class, we can actually, so that way, because this lecture will have all been about how switching factors contribute to power consumption, and the next lecture will be how do we use certain circuits to mitigate switching factor. So clock gating will be that. So does anybody have any other questions? I'm glad we were able to clarify